Yeah, great to have the chance to speak with you all today. I'm going to go very quickly because we got a lot to cover. So basically, this is really how I've come as a climate scientist to think about climate risk and especially kind of the physical dimensions of climate risks. I sometimes imagine like a metaphor of a person sort of standing along a shoreline. And I think the first story is what I call sort of the linear story of climate change. This is the story of historical trends that we've been observing in average temperature, sea level. It's a story of looking at historical, statistical, empirical relationships between sectors like real estate, like ag, and different climate variables. And what we'll see quickly through that first wave is even if we sort of get lucky, if you will, and experience that sort of well-behaved kind of linear story of climate change, we're not at all well prepared, even as it's also true that leaders such as you all are now, I think, making really good faith efforts to try to engage around that linear story of change, try to prepare for those risks to supply chains, to workers, to assets. But it's still going to be really, really challenging under that best case scenario, if you will. But I think as climate scientists, one thing that's really getting a lot of our attention these days is this idea that as we're sort of looking out, again, sort of towards the ocean, it's becoming clearer that there's this second wave of climate change, climate risk, much bigger, much harder to say exactly how big these waves are, exactly when they're going to arrive. But this is essentially the story of nonlinear climate change, the idea that the more you nudge a system, increasing greenhouse gases in the atmosphere, making temperatures higher, the more you start to see cascading impacts and surprising behavior that our best models that are being developed have trouble really sort of capturing. So we'll spend quite a bit of time talking about the implications of that, sort of fundamentally that we're almost bound, I think, to underestimate the economic costs of climate change. But the good news is, I think we can still have hope that this third wave, if we sort of turn away from the ocean and look inland in this metaphor, this is the wave of nonlinearity in the solution space. This is the question of, could we see emissions reduction technologies, adaptations to existing climate threats that are dropping so quickly in cost and really sort of gaining uptake by the business community as some of the traditional approaches that don't protect against risks start to sort of look like losers. That's the hope, even as we are facing a lot of headwinds, to be sure. So that's the frame we'll use to sort of quickly go through this talk. So Bruce, already mentioned the LA fires, and this is, a lens, sort of thinking about fire, to think about all three of those waves that I just mentioned, right? On the one hand, the linear story would say, we've known for a long time that higher temperatures would increase the risk of fire, just as they are. You make the atmosphere warmer, basically a warmer atmosphere can hold more moisture, so it's going to be better at sucking moisture out of the soil, out of the vegetation, out of our crops, even if the amount of rainfall didn't change at all. That's been well understood for a while. So that would be the sort of like linear story. But the real story, I think where we see the complexity and the nuance and a sort of fuller picture is when we start to realize that our models may have underestimated just how much fire risk would change, just how quickly we could see vegetation drying out with just small increases in temperature. And even more to the point, it's the complexity of these cascades, right? We can't just be thinking anymore about how is a tree going to be affected by higher temperatures, right? We're learning more and more about the complexity of all these interactions, right? About how the health effects not just of high temperatures in isolation or air pollution from fires in isolation, but the nonlinear relationships between them. The nonlinear impacts on property values potentially, fiscal sort of bond debt spirals that might emerge, even for houses that don't sit in a particularly at-risk zone. Those are the kinds of complexities that I think are inherently almost impossible to fully quantify. So we need new approaches that face some of those uncertainties, start to explore in a qualitative way some of these emerging relationships, and find ways as we turn to those solutions around adaptation and mitigation that are robust to of different futures, right? And then sort of, from that adaptation solutions perspective, it sounds crass to say, but of course these types of huge shocks do cause people to sort of reassess their risk profile and can motivate and give us chances to do things sort of in new ways. Okay, a little more of this framing sort of, because that kind of second wave that I've been talking about, that nonlinear wave, is sort of a relatively new idea. I want to just sort of explore that a little further, first with a very old quote from 1929. The old world is dying and the new world struggles to be born. Now is the time of monsters, right? You can think about that in a lot of ways with so much sort of disruption right now around the world. And then this notion is described in the book Anti-Fragile, the idea of the mental defect called the Lucretius problem. The idea that the fool believes that the tallest mountain in the world will be equal to the tallest one observed. It's really, really difficult for us to sort of have the imagination and to sort of appreciate that things, even before climate change, could happen that haven't happened. Climate change, as we're going to see, shifts these risks dramatically. And it's very hard to sort of even envision, let alone have the sort of motivation to act before those changes. And then a little more tangible example that sort of gets into this complexity, this quote from the author of Fire Weather, quoted in Inside Climate News a few months ago. Between 2020 and 2024, 50 insurance companies withdrew coverage from Florida and Louisiana alone because of hurricane and flood risk. Insurance is the foundation of capitalism. You don't invest in something like a car or a house or a pipeline or a cruise ship unless it has insurance. If the insurance company won't cover it, are you still going to take that risk? You're going to change your behavior, and it's going to change our economy, which will change our civilization, right? So getting at some of these ways that sort of hint at how it's never going to be as simple as just sort of saying, is a building, is an asset in the flood zone or the fire risk? We can have these cascading hazards and risks that are emerging and inherently hard to quantify. Okay, so now let's quickly jump into the straightforward piece, a story I suspect you all have heard before about the linear story of climate change. Even under this scenario, we see huge impacts that we're still not fully prepared for, right? So this is your sort of classic slide showing that we've had roughly 1 degree Celsius of global warming. Each of these bars is global average temperature averaged across the surface of the planet over a full year. So you can see 1 degree of warming over that period going back to, and on my glasses on, about a little over 100 years. And you can see that there's year-to-year variability. But the idea being what sounds like very little warming, 1 degree Celsius, has completely shifted the statistics, right? The 8 most recent years, this went through 2022, the warmest on record. So small shift in average, huge shift in the statistics and the probabilities. When we built a lot of our infrastructure, we were building for a climate that sort of no longer exists. But to really see that the most, we go in and look at extreme weather events, right? That's where we see the biggest societal impacts, the hottest days with the heaviest rainfall. And just with the most sort of superficial, kind of simplistic, very linear story, we can see a distribution. With climate change, that normal curve shifts more to the right. We get more of these really hot days as shown on the x-axis. The probability shown on the y-axis of very high temperatures can increase a lot with just a couple degrees of global warming. You don't need to invoke crazy sort of nonlinearities and feedbacks to see the hottest days, for example, occurring much more often with just a couple degrees of global warming. And that's, of course, where we'll see the biggest societal impacts too. And just this is probably like the most technical slide to go through, but I think it makes this point well in the context of sea level rise. So what you're seeing here on the left is these coastal locations all across the United States from 1950 to 2020. And you're seeing on that vertical axis, which also is shown in color, it's the same information, how the frequency of nuisance flooding events, right? So this is where there's no storm involved. These are the kind of events that maybe put water in people's basements, mean someone can't open a business, maybe can't take a coastal road home. Those events with just a little bit of sea level rise, like we've had less than 6 inches of sea level rise over this time period, their frequency has gone up tenfold. They used to be things that maybe you can manage, and it's just a nuisance for people if it's happening once every 2 months or so. When it's starting to happen once every 5 days, that's a big change, and that's what we've observed. And then the image on the right is a little bit different take, but very similar. This is, again, the linear, very well-behaved story. So the image on the left, that's just historical data. It's just how a little bit of sea level rise profoundly increased the frequency of nuisance flooding. Here on the right, we're seeing the effect of a small amount of sea level rise projected in the future, just 1 or 2 feet of sea level rise. That'd be a best-case scenario. And the information on the right is not assuming any change in hurricanes or nor'easters. It's just the storms of the past with a small amount of sea level rise. And each of those dots is showing you each location along the US coast has a 1 in 100 year high water level. For New York, it's in the ballpark of the amount of surge we had during Hurricane Sandy. And the idea is that small amount of sea level rise, 1 or 2 feet, turns that high water level, which used to happen once every 100 years by definition in all these places, into something that's happening, in the case of the red, every year or two, with just 1 or 2 feet of sea level rise, not invoking stronger storms. Everywhere you look here, you're getting to where within the lifetime of the typical home mortgage, you're going to be having flooding that historically was once every 100 years, right? The kind of thing that would determine whether you could get zoning, whether you could, and just sort of risks of events like these surges. So this is the linear story. We're already locked into major changes under the best case scenario. And there's more and more research that's pointing to some of the economic impacts of this. This was a really important paper. Justin Mencken was a postdoc at Columbia a few years ago, basically looking at just historical data from 1992 to 2013, and only looking at the 5 hottest days per year, right? So it's not looking at other types of extreme events. And basically what they're showing on the left is how much GDP was knocked down over that 21-year period relative to what the growth would have been due to the extra 5 hottest days per year, those being hotter than they would have been in the past. And the numbers are huge. You see a lot of the global south, 8% ding per year in GDP. And if we aggregate, again, over just that historical data, that 21-year period, the global estimate between $16 and $50 trillion of lost economic output, just because of the 5 hottest days per year and not going into the future at all. So these are big numbers, and this is very much the linear story. Okay, now let's devote a little bit of time before we have to go talking about this second wave. I think this is going to be closer to a real depiction of things than that story that I just told. This is the story of extreme events that were more extreme than we thought possible at today's level of greenhouse gases. This is the story of changes that our climate models said wouldn't be possible at the carbon dioxide levels of today. And it's the story of the need for reinsurers, really anybody sort of trying to be a risk steward, to think about emerging correlations as global warming happens, where we'll see these simultaneous extreme events more often. Because of the nonlinearities, as these events become more frequent, you really run the risk of sort of breaking the bank, whether it's an emergency management response, whether it's insurers, reinsurers. These risks are growing very quickly. So quickly walk through a few examples. We saw earlier global average temperatures. This is essentially almost the same figure, but now it's sort of drawing attention to the last 2 years. We've added 2023 and 2024. So one could still say, oh, the last 10 years have been the 10 warmest years on record. That's true. But arguably, there's another story here. These really hot years happened at a time when we don't have natural variability like an El Nino event that makes things warmer to explain it. This surprised climate scientists a lot. Is it hinting at missing processes from our climate models? We don't know for sure. But there's growing concern that maybe we've perturbed this system so much that's not responding the way it used to. As the oceans warm, they're not as good at mixing and sort of taking up heat from the atmosphere and maybe taking up carbon dioxide too. We don't know for sure, but from a risk management perspective, these are growing concerns, tail risks outside what models would suggest. Similarly, we've had these extreme events, right? The Pacific Northwest heat wave, late June 2021. Temperatures were 50 degrees Fahrenheit above average. If you'd polled climate scientists, none of them would have said that's the region or the season when we're going to see temperatures 50 degrees above normal, right? So it wasn't just the shock of what those temperatures were like, it's these emerging correlations in the impacts world, right? We had fires at the same time, cities burned to the ground. We had hydropower not available for air conditioning, for example, because the heat before that had dried things out so much that you didn't have that energy capacity. You had fire interacting with temperature to create, health risks for people. So all around the world, we have to ask, are we prepared for these sort of emerging interactions and correlations and cascades? Fire across Canada, 2023, area burned, that's the red line. The black line is the area burned in prior years, right? It looks completely different. It's completely different behavior. Is that due to higher temperatures drying out regions, making them prone to fire in a way that they weren't in the past? Climate models don't predict this, right? And we saw the impacts extending, right, to us. Okay, single most important slide to sort of take away information from here. This is IPCC reports. AR5 was the IPCC report from 2017. AR6, the one from 2022 or so. So about 6 years passed between these We have these critical systems like aggregated systems, global impacts. Basically what you're seeing here on the y-axis, an amount of global warming, right? There's that 1.5 degrees Celsius target that we're right about at. The key takeaway here is to focus on these dashed lines going down. Do you see those? Basically, that's telling you that where you see like a red color, that is a level of risk that we may not be able to adapt to as a society. That might like push us to the brink of what we can handle. And over the course of those 6 years, temperatures actually didn't warm that much. What happened is all the world's leading experts in these various sectors completely shifted in their perception of how much temperatures will be associated with catastrophic damage, right? So here, when you polled them in 2016 or so, they said 2 degrees, let's use this example here. They said 3 degrees or so might lead in this global aggregate impact sector to huge changes that we couldn't adapt to. 6 years later, when you polled them, they now said 2 degrees Celsius. See how that's got the same color that it had there? We dropped a whole degree in terms of their assessment of danger, right? So this is these tail risks and surprises. We've underestimated all of these kind of risks. So if you're an insurer, if you're a city trying to prepare for climate change, you can't take a single hazard perspective anymore. You got to think about sequences. You got to think about how climate change could increase the risk, not just of the same type of event like a hurricane, but maybe a fire in the western part of a country, right? Do you have the emergency management? Do you have the insurance funding to protect against more frequent events that will produce bigger impacts as we get further out on the curve because of nonlinear relationships between, say, temperature and agricultural losses? Okay, just sort of wrapping up. It doesn't have to be sort of complex examples. It could just be a single place. Kennedy Space Center, the Space Coast, very vulnerable to storm surges. You have geopolitical, major economic impacts if that one, for the whole globe, if that one place becomes flooded and we don't have sort of preparation for that. Okay, wrapping up very quickly. Ultimately, we're not going to be narrowing these uncertainties, I believe, as climate scientists. We're learning more about all these complexities. The one place where we can narrow the uncertainties is you all. It's the world of really uptaking emissions reduction and adapting. And so some leading experts are starting to say maybe adaptation could be the biggest sort of investment sort of cycle for the next decade or so. We can see more mutual funds sort of leaning into adaptation, maybe. There are, I think, some encouraging signs of tipping points in this space. We know how quickly we have to reduce our emissions. We can't be too sanguine about this. It's an urgent situation. But if we look around, we can see encouraging examples. How quickly we've seen this nonlinear growth in new car sales being EVs. How quickly we've seen generation of solar and wind all around the globe picking up. Right? These are exponential curves working in our favor, arguably happening a lot faster than we thought. Are we approaching that point where some traditional energy systems, traditional approaches to risk management start to look like stranded assets, sort of losing perspectives? Maybe. And especially as we start to look at how these costs have come down, bottom right, lower than the, do you reach a point where even can policy not obstruct this kind of change? And of course, the US increasingly isn't as dominant in these spaces as they are. There's huge innovation happening, as you all know, in a lot of other parts of the world. Price of lithium, look how it's come down in just 11 years, right? Now we have new battery technologies that don't even rely. Okay, let's leave it there. Thank you very much. The last thing I'll say is, by investing in adaptation and mitigation, we can change the future that I described here. That is the pathway whereby we can avoid, that's really the only pathway to avoid these really catastrophic impacts. And I think, looking at some of those curves, it can still be done. It's not gonna be the scientists that are gonna be doing it, it's gonna be people like you all. Thank you.